Right, this video is being made for Mr. Mellinger's AP Chemistry class for the spring review for the AP exam on May the 4th, 2020. So what I'm going to do is quickly review how you do Aufbau structures, and stick with it. If you think you understand this, I'm going to show you some of the exceptions you might not remember. So stick with this video. I'll try to make it quick. First, let's do a basic one. This is boron. So on the periodic table, it's the third element over in the second row. So the first two electrons represent hydrogen and helium in the first orbital, first row. So you put an up arrow and a down arrow. The fact that they're opposite directions is called the Pauli exclusion principle, because they have to have opposite spins to be in the same subshell. Now we go down, and anything in the s orbital is going to be in the first two columns. So lithium and beryllium would be the first electron in the 2s orbital, beryllium is the second electron in the 2s orbital. So we simply come up here, and Aufbau means build up, and that's what we're doing. Each higher level means a higher energy level. And now for boron, it's the third element over, lithium, beryllium, boron in the second row. So we put the first one up. The second one is also up in the next subshell. So the px, then py, and then it's the third element over, so that's boron right there. The fact that you spread these out is called Hund's rule. So don't put 1, 2, 3, 4, 5, 6. It's 1, 2, 3, and then 4, 5, 6. We didn't need to go that far. Okay, the way you would write this very simply is you have, in the 1s orbital, you have 2 electrons, so that's 1 s orbital, and then the 2 electrons, it's not a squared, it's just a symbol for 2 electrons. Then in the second orbital, you have 2 s, 2 electrons, and then in the third orbital, you have 2 p, 3. You don't have to designate px, py, pz, it's just 3 pz. Alright, and that's how you write the electron configuration. The condensed electron configuration is you start with the noble gas that comes before the element you're dealing with. So boron, the noble gas that comes before it in the first row is helium. So you take that noble gas, whenever you get to the end of the 1s orbital or any p orbital, then that's going to be a noble gas. So this is going to be helium. So helium is right here, and then we come across and we write the rest of the notation that comes after helium, and all that is this part right here. So that's going to be 2p3. This doesn't seem much shorter, but it will when we get the elements further down the periodic table. Let's do another one. Okay, so we're going to do aluminum. So here we go. So we find aluminum. So aluminum is right here. It's in the third row. It's the third element over in the third row. So we're going to go ahead and do that. So the first row is hydrogen, helium, up arrow, down arrow. Next we have lithium, beryllium in the 2s. And then we're going to fill the second orbital. So it's 1, 2, 3, 4, 5, 6. But let's draw them in the proper order. It's 1. This is boron, carbon, nitrogen. Then we come up back and start pairing them up. That's oxygen, fluorine, and neon. When you get to the end of a p orbital, with the exception of the first row only, you're at a noble gas. So this would be the noble gas neon right here. Okay, now we're going down to the third row or third period. So you got sodium, magnesium. So that's up and down. And now aluminum, just like boron was, is the 1, 2, third element over. So you go up, 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 and there you go. So go ahead and write this out. It's 1s2, 2s2, 2p6. Now we go up to 3s, 3s2, and finally 3p. There's 3 electrons in the p orbital, 3p3. Find the closest to the end, go backwards and find the p orbital that has 6 electrons. It's this one right here, so you can block that off, and that represents the noble gas neon. So the condensed electron configuration is going to be neon, and then the rest of this. 3s2 3p3. Okay, so that's how you do that. Okay, next up I'm going to do copper. And so where do we find copper? And it is it's right here. Okay, next up I'm going to do copper. So where do we find copper? Copper is right here. You'll notice it's a transition metal. The valley here is the transition metals, and it's the 9th element over in the transition metals. So you have potassium and calcium, but if you just go to the transition metals, it's 1, 2, 3, 4, 5, 6, 7, 8. It's the 9th element in the transition metals. So that's going to have a special effect on this. So we go ahead and we start like we do with any other element. So hydrogen and helium are in the 1s. Up arrow, down arrow. Then lithium and beryllium. Up arrow, down arrow. And then you have the 2p orbital across here. Just get in the habit of drawing them in the proper order like that, even though you know it's going to be filled up. If you're going below the second orbital, you know the second orbital has to be filled. Okay, and you don't have to do this, but it's just helpful. It's just recommended. Keep track. There's neon right there at the end of the 2p. Now you go to the 3s. That's sodium, magnesium. Up arrow, down arrow. And now you're going to go for copper all the way across the 3s. 1, 2, 3, 4, 5, 6. So proper order, Hund's rule. Like that. And now you're at the next noble gas, which is argon. Anytime you're at the end of a p orbital, that is a noble gas. Now you go to 4s. And now a funny thing happens here. You got potassium and calcium. So we're going to put 1, 2, and now we're going to go ahead and we are going to go all the way to copper. So it's 1, 2, 3, 4, 5. So now you're into the 3d orbital. Again, just follow the periodic table across, so you go from 4s to 3d. Remember that transition metal, the d orbital, is one row below its number. So this is the 3d, even though it's in the 4th row. Okay, so we go up, 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 up. Remember, copper's 9 electrons over in the 3d orbital. So now we go down, 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 and down. Now, you would think that we would be done, but we're not. Here's the rule you have to remember. Atoms like to have either full orbitals, that would be like the octet rule, like a noble gas. So they either want full or half full orbitals. So here's an example of that. Atoms like either full or half full orbitals. So here's an example. If you can put one more electron in here, this would be full. Where can you get that electron from? Well, you can borrow it from the 4s. So now you can make the 3d a full orbital, and notice what else you did. While the 4s is no longer a full orbital, it is a half full orbital. So you have a half full orbital here, that's good, and a full orbital here, that's good. Now the next element from copper, by the way, would be zinc. Where would that one more electron for zinc go? It would go back here. It would fill this back in. Okay, let's write the electron configuration for this now. Okay, so let's write the electron configuration for this. It's 1s2. Then you go to 2s, it's 2s2. Then you go up to the 2p, it's 2p6. And we're not going to block that off yet because for noble gas, because there's a higher noble gas we're going to get to. Then it's 3s2. Then it is 3p6. And I can see that's the highest full p orbital I'm going to have. So I'm going to go ahead and block that off. And then I got 4s2, but we erased one, so now it's only 4s1. And it's 3d10. Okay, now we have a full d orbital and a half full s orbital. That makes the atom happy, kind of like the octet rule, and that's the notation. Now this entire thing, we wrote it right here, is equivalent to the electron configuration of argon. That term for that is iso electronic, when the two electron configurations are the same. They're said to be isoelectronic, meaning same electronic structure. So there's argon. So everything in this block is represented by AR. Then you have 4s1 and 3d10. Okay, stick with me on this video because there's going to be a couple more tricks to come. Next, let's do chromium. All right, here it is. It's also in the 3d orbital, and it's 1, 2, 3, 4 over. So let's go ahead and start filling these in. You can do this quickly now. Again, I'd like you to still do it in the proper order, just for good habits. 3s. Whoops. There you go. 3p. Okay, and that is argon again. Then 4s. And now it is in the 3D. It's 1, 2, 3, 4 places over. 1, 2, 3, 4 positions over. And that would be chromium. But again, we'd like to have either a full or half full subshell. So if we can add one more electron here, we can make it half full. Where do we get it from? Same thing as with copper. We take it from the 4s. So now 4s has a half full, and the 3d has a half full, so everybody's happy with that. All right, so electron configuration. Okay, so it's 4s1 and 3d5. Again, argon is going to be our noble gas for this. So just remember those exceptions for filled subshells and half-filled subshells. Okay, let's do another one here. Let's do a vanadium 2+ ion. Okay, so we're going to do V, and it's going to get ionized. Metals always become cations. They always lose electrons. So we're going to do V2+. Okay. All right, so here we go. Up, down, up. Okay, it's adding an electron does not give it a complete half shell, so that we're not going to do that. So this is the electron configuration for vanadium. But what happens when it ionizes? That it loses 2 electrons. The answer is you do not take them from here. You take them from the 4s. Yeah, it's just something you got to get used to. It's the 4s that's going to ionize first, not the 3d. So you're going to take them from here. You got to take away 2 electrons. That's what the 2+ is telling you. You got to take away 2 electrons. So I've taken them away from the 4s. So that's going to be the electron configuration of a 2+ ion of vanadium. So it's going to be 1s2, 2s2. Now there's alternate ways you can write this. And by the way, when you're writing it, you don't necessarily put these brackets. I'm doing that to show you that that's where the noble gas is. You can either write it as 4s0, just to account for the 4s orbital, and then 3d3, or you can omit that altogether. You don't have to write that in there. Okay? So it's one of the quirks of the Aufbau that you're going to have to remember when you're ionizing a transition metal. You take off the s electrons before you take off the d electrons. Okay, next up we're going to do cobalt. This will be the last one we do, because we're pretty much going to have covered all of the exceptions and anomalies in the Aufbau. So cobalt, we find it again, it's in the 3d orbital. There it is. And we're going to make it a cobalt, or CO, 3 plus. It's going to ionize. It's going to lose 3 electrons. So see if you can figure this one out from that. Okay, so cobalt. These are filled. And now we're down to the 4s. So cobalt is in the 4th row. It's a 3d orbital though, so it's going to fill this. And then the 3d, it's 1, 2, it's up here, 1, 2, 3, 4, 5, 6, 7. 7th element over. So here we go. Okay, and there's cobalt. That's what cobalt would look like. It can't half fill anything by borrowing an electron, so it's going to stay like that. But now we're going to lose 3 electrons. Okay, so which 3 do we lose? The first 2 we lose are in the 4s orbital. And when you ionize a transition metal, you take out the s electrons first. That's 2. Now we need a 3rd one to come out. Be careful, it's not this one. Although that would give you the same electron configuration notation, but it's not this one. This was the last electron we put in right here. So we're going to take that out. So now we've taken away 3 electrons from cobalt. So let's write the electron configuration then. And it is. Again, there's our highest noble gas right there. There is no 4s. And there's 3d, 1, 2, 3, 4, 5. There's 6 electrons there. If you want, you can write optional 4s0, 3d6. And condensed is again going to be argon as the noble gas. Okay, so that takes care of it. That's how you do Aufbau. That's how you take care of the d orbital when it's half full. When you can add an electron to make it half full or add an electron to make it all the way full, you borrow that electron from the previous s subshell. If you're going to ionize a transition metal, you take away the s electrons first, and then you take away d electrons after that. Okay, so that covers pretty much Aufbau, Hund's rule, Pauli exclusion principle.